We've now learned about the basic operators of vector calculus, the gradient, the divergence, and the curl operator, and also the Laplacian. In particular, the definition of the curl operator might be a little bit perplexing at first. I would like to introduce a formalism related to what is known as a nabla operator that might be helpful to make sense of these different definitions. In particular, it will relate the gradient, the curl, and the divergence to some operations that you already know from linear algebra, or more precisely, to some things you know from high school geometry. We can summarize gradient, curl, and divergence using the so-called nabla symbol, which is written as this inverted triangle. And we think of the nabla symbol as an n-dimensional vector whose entries are formally the partial derivatives in the direction x1, x2 up to xn. So we have got nabla equal vector containing del1, del2 up to del n. And sometimes we also like to write it with this vector head on top. A word of caution here. Usually we do not put partial derivatives into a vector. Usually we only put numbers in there. We don't even have a specific notion mathematically. We'd have to justify first what does this vector actually mean when we put in partial derivatives. But for the time being, let's just ignore these issues. Let's just see what formally we can do with this type of nabla vector. So this guy is called nabla. And let us pretend formally that we can just use such a vector Let us now have a look how we can relate the notion of gradient to the nabla vector. The gradient of some function f, well, that's given as the partial derivatives in each direction. Del1 of f, del2 of f, up to del n of f. And purely formally, I can write this as, well, we take the nabla vector and multiply it with the function f. That is modeled after the geometric operation of multiplying a vector with a scalar. Formally, it looks like we multiply the nabla vector with the scalar f, formally. The divergence of a vector field f can also be related to the nabla symbol. If I take the divergence of f, okay, that's the same as summing up del1 of f1 plus and so on up to del n of fn. If I take a sharp look now, I recognize this can also be written as a formal dot product, a formal scalar product of the nabla symbol with the vector f. Formally, this is modeled after the dot product or the scalar product. Also known as product scalaire or scalar product. Finally, since we have already done the gradient and the divergence, the Laplacian can also be expressed as an operation using the nabla vector, the nabla symbol. We just have the Laplacian of f equals, formally speaking, the divergence, which is a dot product with nabla, of nabla times f, the gradient. These calculations using the nabla symbol have been purely formal. In some sense, we step out a little bit out of mathematical rigor and just use the nabla symbol with the partial derivatives in each component, just like we would use a vector. That is extremely helpful, and it is very common in the literature of physics and engineering, and even mathematicians do it when no one is watching. And finally, we talk about the curl operator in 3 dimensions. It also can be related to the nabla vector, namely in the following manner. In 3 dimensions, the curl of a vector field f equals the cross product of nabla and f. So let's write this down formally. Got the curl of this vector field, and I write it down first as a vector in terms of partial derivatives and the components of f. The first component of the curl of f is del2 of f3 minus del3 of f2. And the second component, we remember, we need to put a minus sign here first, is negative del1 of f3 plus, this time, del3 of f1. And lastly, the third component equals del1 of f2 minus del2 of f1. If you now take a sharp look at this vector, you recognize that formally, just formally, we can write it as the cross product of the nabla symbol and the vector f. We got nabla cross product the vector f. The formal operation here is the cross product So just like we can connect the gradient with scalar vector multiplication, and how we can connect the divergence with a scalar product of nabla and some function, we can relate the curl of some vector field as a cross product of the nabla symbol and the vector field itself. Personally, I think of these relations as some sort of memory device. Whenever I want to write down the curl of a vector field, I just keep in mind it can be written as a cross product of the nabla vector and the vector field f, and then the formula is completely clear. The nabla symbol is extremely helpful for practical computations, even though, formally speaking, we leave a bit the grounds of rigorous mathematics. But that's okay, in practice it helps. There's one more thing I would like to discuss in relation to the curl operator. In terms of rigorous mathematics, this is even shakier than the nabla symbol, but it is just very helpful sometimes when you do practical computations. We can express the curl of a 3D vector field as a formal determinant, whose entries involve vectors, partial derivatives, and some components of the vector field. Formally, the curl of a vector field, cross product of nabla and f, can be written as the determinant of a 3 times 3 matrix, whose rows are as follows. The first row contains the unit vectors, which is usually something we don't do, but here we're allowed to do it. The second row contains the partial derivatives. And finally, the last row contains f1, f2, and f3. As a brief reminder, what are the unit vectors here? Well, we can draw our 3D coordinate system Then the first coordinate vector is E1 with entries 1, 0, 0. The second coordinate vector is just E2 with entries 0, 1, 0. And then E3 is the vector containing 0, 0, 1. Those three vectors are put into the first row of this determinant, formally speaking. The second row contains partial derivatives, and then finally the last row contains the entries of the vector field. Arguably, this is a very unusual determinant, and it is only used for the purpose of formal computations. But for the time being, we ignore such issues, and we take a look how we can recover our formula for the curl operator from this determinant here. The formal computation starts with the formal determinant. So we take the determinant E1, E2, E3, del1, del2, del3, and F1, F2, and F3. Let's now do a Laplace expansion of the determinant using the first row. If we just do that formally, well, we get E1 and the 2×2 subdeterminant del2, del3, and F2, F3. And we get minus E2. There's the next component. Del1, del3, and F1, F3. And then plus again E3 multiplied with a subdeterminant del1, del2, F1, F2. As we multiply out those subdeterminants, we get E1 multiplied, well, del2 times F3 minus del3 times F2. Similarly, we get negative E2 of, well, del1 F3 minus del3 F1. And lastly, we get E3 multiplied with del1 F2 minus del2 F1. What we now have here is several vectors multiplied with these scalars here. For example, here we have got this derivative of F3 in the x2 direction minus the derivative of F2 in the x3 direction, and so on. And now we can just use our usual mathematics again. We put everything here into a vector. And so we get, well, del2 of F3 minus del3 of F2. It's already the first component of the curl. Looks good. We get negative del1 F3 plus del3 F1. Very good. And lastly, we get del1 of F2 minus del2 of F1. And now we recognize, yes, that's the curl of F. That is yet another way of memorizing the formula for the three-dimensional curl operator of a vector field. So far, this has been a purely formal computation. It is very common in science and engineering, and sometimes even mathematicians do it.